It is our great pleasure to have Quentin Peyron speaking today. Quentin is a postdoc with Jessica and did his PhD, as I now practice, at UBFC in Besançon, working with the MINAROB team at Femto-ST. Quentin, can you say in the beginning also a few words about these teams? It will be very interesting. And you were also working with AVR team at iCube in Strasbourg. And you also collaborated with MSRL at ETH Zurich, so you had a lot of great collaborations. So during his postdoc, Quentin also received the postdoctoral fellowship award from the University of Toronto, and you're working on improving the deployment of endovascular robotized catheters using continuum robotics modeling and path planning methods. And since January 2022, you will be a permanent researcher at INRIA. Congrats, INRIA is a really amazing place, and I'm really looking forward to see what you will be doing there. And you will be working there with the DFROS team on eco-designed parallel continuum robots for industrial applications. So now we're looking forward to hear your talk on elastic stability issues in continuum robotics and how to snap out of them.
Thank you very much, Igor, for this nice introduction. I will definitively talk about the different labs I worked with in a bit. All right, so it's my great pleasure as well to present you part of my research on continuum robotics that I mainly worked on during my PhD, but that I had the opportunity to work on as well with Jessica this year. And which is focusing on these elastic stability issues that we have in continuum robotics and how to avoid or to control them. So first of all, let's begin with the beginning. Just a quick recap. Some of you might already know them already well, but continuum robots are robots that are not composed of rigid classical links and joints, but that are composed of a compliant slender structure that we are going to deform in order to produce motion. And basically the deformation will be distributed along this structure and will be due to actuation forces, but also to external forces, as you can see on the video. So these robots have a number of very interesting properties. Because they are not composed of these classical rigid joints, then can be designed at quite small scale, at the millimeter scale in particular. They can be deployed in cluttered and tortuous environment because of their continuous tortuous shapes while being dexterous. And they have this intrinsic compliance, which allows them to deform in the contact of in the contact with the environment instead of damaging this environment, which of course is very interesting for human-robot interactions. So they have been successfully considered for different kind of applications which have this need of deploying into confined, unstructured, and sensitive environments. One of the most considered application is minimally invasive surgeries, where there is a need for deploying medical tools through keyholes or through natural orifices, and then deploy these medical tools inside the tortuous and narrow cavities of the human body in order to reach a surgical site, which is here at the base of the skull on this video. Another nice application at a much larger scale now is search and rescue application, where we need to access victims under piles of debris or in disaster area, so which are hard to reach with conventional means. Then continuum robots can provide very interesting solutions to detect this victim and also bring them some supply, for example, or to rescue them. So they have these continuum robots have a lot of nice properties, but of course there are a number of challenges behind their use. And in particular, they are most of the time controlled in a quasi-static way in order to ease their control, because the dynamic control is pretty complex. But still, quasi-static control is still challenging today due to the particular kinematic properties of these robots. So let's go over them with this, let's say for the moment, generic planar continuum robot that you can see on the schematics. So one first property is that the shape and the behavior depends on, so the, as I said before, on the actuation forces that are used to bend the robot, but also on external forces, such as the gravity, such as the load at the end effector of the robot during manipulation. And that's why we need to account for these external forces, and then we don't speak about a kinematics model, kinematic behavior or kinematic model of a continuum robot, but we often refer to a kineto-static or geometrico-static model. So that includes geometry and forces. We also often say that these structures have an infinite number of passive degrees of freedom, which means that I can, if I take one point along this structure, I can generate motion by applying the right forces on this compliant slender body. So in other terms, you could imagine to approximate your robot by these like successive revolute joints, as we can see on the graph, and try and imagine that this number of joints tend to infinity. And is basically what we mean by infinite number of passive degrees of freedom. Of course, we cannot actuate all these degrees of freedom, so this structure is underactuated. And because it's flexible, during its motion, the robot will deform and accumulate potential energy. So you can imagine to have torsion springs at each of these revolute joints along the structure. Due to all of these properties, one particularities of continuum robots is that they can have elastic stability issues. So during the motion for specific design parameters and for specific actuation inputs, they can have actually multiple configurations for the same actuation values. And they can snap suddenly, so become unstable and snap suddenly from one configuration to another, as you can see on the video for a particular kind of continuum robot here. So these phenomena are referred as buckling in the community of the more structural mechanics. And also, they make sense to have like this multiplicity of configuration because we know we have the same issue in standard rigid mechanisms that have these passive joints. If you take, for example, here, the 5-bar planar mechanism, where the two left and right joints are actuated, then I have a passive joint on the middle that can be positioned either up or down. So we have two different configurations for the same set of actuation values. So these elastic stability issues have undesirable effects. As you can see, the motion are uncontrollable and sudden, and you don't want necessarily this robot to snap in your nose when you're actually performing surgery. So they can generate dangerous motions, and also part of the workspace is not reachable anymore because some robot configurations are unstable and cannot be reached physically. So there is a need to predict these phenomena in order to be able to avoid or control them. And that's basically what I would like to discuss with you this morning. The work I mainly did during my PhD on this. So we'll present you a numerical framework that we developed in order to analyze in a generic way these unstable phenomena. And then I will present you a succession of results that we obtained on different kind of continuum robots. Some elastic stability issues that are actuation dependent, some others that are due to external forces, such as gravity, and then present you the last results that we obtained on how to manage the stability in an active way in a paper that just got accepted to IJRR. And so you have the references to the papers here, and all this work has been performed in collaboration between 3 labs. So the FEMTST laboratory in France, in Besançon, which focuses on medical devices, but who also has an expertise in micro robotics. They do, the three labs do very cool stuff, so we can discuss about it more afterwards if you want. But, the EQ laboratory, which has, and the AVR team, which is specialized in medical robotics, and in particular interventional robotics, when you have to have compact system to go inside MRI machines, for example, or X-ray scanner. And the MSRL robotics of the ETH Zurich, which is working on basically macro robots and magnetic catheters that using this magnetic actuation. So yeah, I guess let's get started with the numerical analysis framework. And as usual, I forget to launch all the videos, but we are going to see basically robots jumping all the time. So stay tuned on. All right, so the current way of analyzing the stability of these robots is to analyze a kineto-static model of these robots. So how to model in a generic way these robots? So first of all, we usually approximate the shape of a robot by a one-dimensional curve that you can see in dashed dotted line here, which is called the backbone. And basically what we do is we define a moving frame along this curve, which is located at a specific arc length, S, and the pose of this frame with respect to a base frame, and also the curvature, the local curvature of the robot will define the pose of the robot and its shape, and that's what we are going to control and look at in the following. And then we need to derive a model that relates this pose to actuation, displacement, and forces, but also external forces, which can be distributed along the structure, such as the gravity forces, or very localized at certain point along these robots, such as like manipulation forces at the tip. So we try to relate these using also the robot mechanical properties, such as the stiffness. And to do that, one solution is to express the total potential energy of this system, and then to using the laws of physics, and then to use a first variation principle or the Lagrange formula with respect to S to obtain equilibrium equations.
Quentin,
yes.
May I ask a question? When you say you want to control local curvature is typically, it is not constant throughout the robot. So how do you go about discretizing it? Like, do you just control local curvature at certain points, or do you try to, is there a way to control it like at every point in a certain way, but then you have constraints?
This is a good question. So this is about like this shape control of continuum robots, which is not what people begin to work on this now, but they usually like just focus on the end effector position and orientation. But basically what people try to do is to approximate the shape by either segment with constant curvature, and then you have for each of these bending segments one value of curvature that you try to control. Or some people try to approximate the whole shape by polynomials, for example, and then you want to do the control in the parameter space of the polynomial, basically.
But what you're saying is for your work, you don't care as much about the shape as about the end effector position.
Yeah, so I said we are going to control it. It's a generic way for continuum robots. I'm not doing control in this work particularly, or on what I will present here. But yeah, in my work, I mainly focused on the end effector. I didn't do like shape control necessarily, but that's pretty neat. Yeah, going back to it, the final model that we obtain usually with this like kind of generic shape representation and generic robot design is a boundary value problem, so a set of nonlinear equations that have mixed boundary conditions. And basically, it's not possible, in general, not possible to solve these equations analytically, and very difficult to analyze them analytically. So there are two different approaches currently to analyze stability, which is either to still try to do analytical derivations, but considering quite restrictive assumptions on the robot design. And so the results you obtain are specific to these robot designs. Or to go for numerical solutions and try to solve numerically these models using standard numerical solvers. So this allows to like take account generic general robot designs, but with the current numerical solvers, the convergence depends on the initial guess quality. And also there can be convergence problems near unstable configurations. So in our work, we propose to go for the numerical approach and to propose a numerical framework that is more adapted to study these stability issues. So basically what we do is, first of all, to reformulate a bit the boundary value problem, we discretize spatially the robot along its backbone. So with a finite number of nodes along each of these segments that you can see here. And basically this will give us a set of nonlinear equations here, because all the derivative will be expressed within differences that will be easier to solve and to analyze with numerical tools. And we apply to this model a set of off-the-shelf numerical tools to analyze the stability. We first of all simulate deployment using a numerical continuation method. We then detect during this deployment the appearance of multiple configuration of the robot using bifurcation analysis, and we evaluate the stability of each of the computed configuration using the Hessian matrix of the potential energy. So I won't have the time to go through all of these points, but I will go through the two most important ones, to my opinion, because you need them to understand the results afterwards. So the goal of the continuation method here is to simulate deployments, so to vary one actuation input of the robots, and then to compute the corresponding set of robot configurations. And we are going to assume that these robot configurations evolves continuously according to this actuation inputs, and will give us a branch of solution of the kineto-static model, a set of solutions or a branch of solutions. So basically what we do is the method works with a prediction correction process where we start from one point. We increment the actuation input along the local tangent of this branch of solutions, which give us a prediction. And then we correct this prediction using a Newton-Raphson algorithm. So basically, it's what we do for the first point here. So we obtain the next point on the branch, and we can do it for the next iteration, taking the local tangent of this branch of solution, this curve that you can see here, predicting, stepping along it, predicting, and then correcting using the Newton-Raphson algorithm. Now it might happen that this particular curve that we can see here has actually a higher curvature. So this kind of first order predictor for the next robot configuration is not accurate anymore. And then the convergence of the Newton-Raphson method might not be ensured. So in order to deal with that, we add to this method comes with a step size control, where if the number of correction iterations increase along during the computation, then we reduce the incremental step. And if this, because we have more difficulties to converge, and if this number decreases, then we converge more easily, and so we can increase this increment step. And this basically allows us to compute successive robot configuration while ensuring that the initial guess for this numerical solver is ensure convergence. And also we can compute easily stable configuration and unstable configurations, which is in practice not super easy with other numerical solvers that do not have this prediction process, because you might converge more easily towards a stable configuration rather than an unstable one. So the second tool that we use is bifurcation analysis. So during this computation of these branches of solution, we try to detect particular configuration for which multiple solutions appear, or for which the robot changes stability. And basically, there is a whole field which is bifurcation analysis, which tries to categorize behavior changes in dynamic or static systems. And there is in particular two kinds of bifurcation that are relevant and interesting for us, which are branching points, where we have two branches that actually intersect at one single point, and limit points, where we have these vertical tangents along the curve. Basically, bifurcation analysis will provide detection function to be able to detect these particular points. So for branching point, we monitor the Jacobian matrix of our nonlinear set of equations. And if this Jacobian matrix becomes singular, that means that we have a branch point here. And for the limit point, we look at the local tangent of the branch with respect to a certain arc length SV along this branch. So this is great because these functions are general, like applied to a model, which is general to a lot of designs of continuum robots. And also, this allows to detect this configuration where we could have convergence issues with standard like Jacobian-based numerical method. And instead, we can use a more security robust root finding method, such as the second method. So we have a method that ensure that we converge even if we have convergence, even if we are close to these stability issues. So finally, the goal of this whole numerical framework is to compute these bifurcation diagrams. So we start from an initial simple configuration of the robot. So like simple, for example, a robot which is completely straight, which is not deformed. And then we are going to grow this diagram from this configuration, computing, for example, here in this particular case, the first branch, which is completely straight horizontal, detecting any appearance of second branch of solutions, so any branch point here. And then from this branch point, computing the second branch and growing the second branch as well. And we evaluate stability on the fly with the Bayesian matrix that I did not detail before. So we obtain a graph that basically this kind of map of possible configurations for the robot, which contains the information we need, so the elastic stability of this robot, but also the possible configurations it can have during the deployment. And then we can obtain this bifurcation diagram for using our generic kineto-static model, so without doing a lot of assumptions on the robot design stuff. By the way, these off-the-shelf tools are available on MATLAB, free MATLAB toolbox. Of course, you still need to have MATLAB, but a toolbox called MATCONT, which contains the continuation and the bifurcation analysis. So just to reproduce the results and to analyze systems, it's very, very convenient and interesting.
So for this bifurcation analysis, where your robot knowledge goes in, is basically the system of equations that you built.
Yeah.
And then for you analyze it like with the standard bifurcation analysis tools, like looking at determinant of this,
exactly,
of the Jacobian.
Yeah. Yeah, this is whole off-the-shelf tools that we try to gather and to apply to this continuum robots, and we depend on this model indeed.
And basically, the research problem here is finding a good model so that the bifurcation analysis is meaningful. or finding good model parameters.
So this is basic. This is why this is one of the challenge to have a generic model to account for this wide range of case studies, case scenarios, robot design, etc. But I would say the base research question is we needed tools in order to analyze this phenomena for different kind of robots. It's just like we did not contribute on like providing a new algorithm, for example, but it's more like using what is already there. And by the way, these tools are often used in structural mechanics to study buckling. So we kind of translated them to continuum robotics.
Yeah.
All right, I guess it's time to see some robots flipping, to robot snapping. So I propose you to guide you from some of the results we had on 3 kinds of continuum robots. Concentric tube continuum robots, magnetic continuum robots, and then the great fusion of these 2 principles, which give a magnetic concentric tube robots. Let's go. So concentric tube robots, for those who do not know them already, are consist of a telescopic assembly of precurved and elastic tubes. So each tube is precurved. You assemble them in a concentric way. And by rotating and translating these tubes with respect to each other, this precurvature will interact and will provide different robot shape, this kind of tentacular motion that you can see on the video here. These robots have a lot of great properties. They are one of the thinnest continuum robots that we can make because they are just the manipulator part. We don't see the actuation unit with all the motors in this video. But just the manipulator parts can be for free tubes, for example, 6 degrees of freedom, 1 millimeter wide maximum. So it's very thin. And also an interesting property is that they can perform what we call perfect follow the leader behavior and deployments. So basically, for specific shape of tubes, a specific disposition of tubes, we can deploy the robot so that its body follows the same path as its tip. So it's the same principle when you have mobile robots and you have one leader and the other mobile robots behind that has to follow the same trajectory as the leader. So here we have an example of deployments where the robot body is following the robot tip, basically. And so for these robots, this happens when you have tube with constant curvature that have this arc of circle shape, or constant torsion. We will see it just afterwards. And when there is no torsion deformations. And so this happens, this no torsion deformation, when the tubes are aligned or are in opposition, which will give more this S-shape path that you can see here. So the problem is when, famous results of the literature is that when you have these 2 tubes in opposition, you can actually encounter stability issues during the deployment. Basically, what we do is we assemble the tubes and we increase this interaction length, delta L2 here, so the deployed length of the robots. And then everything goes fine at the early stage of the deployment. At some point, we encounter bifurcation here, and the robot becomes to experience torsion and have different configuration for the same actuation values. And basically, we know that I have to stop saying basically, it's horrible. I apologize for that. We know that the robot follows the leader behavior on this specific portion before the bifurcation. So we know that we have this problem for 2 tubes continuum robots composed of constant curvature, and we can analyze it analytically, but with the same tools, we couldn't analyze the stability of robot composed of more tubes, like 3 tubes, or composed of these more complex helical tubes, which have like constant curvature and constant torsion. And so that's basically where we came into play. So we used our numerical method to analyze these two case studies. And for example, for the example of the free tube CTCR, we could draw these 3D maps where we draw the robot configuration in terms of this particular roll angle that we can see here, according to the deployed length of the robot. And then we begin to vary delta L3, which is the first section of the robot, which is the black curve. And then for each point of this black curve, we can vary delta L2 here. And that will give us this kind of pitchfork diagram that we see here. And we could observe that we could evaluate this area in the actuation space where we can actually do follow the leader behavior. And we can also evaluate the maximum configuration of the robot during a deployment, which is a maximum of 3 different configurations. Also, we analyzed like the case with helical tubes, and we saw that this constant torsion that give us this helical shape does not actually have an influence on the robot stability. So basically, you can increase this initial torsion of the tubes. You can have different shapes and more complex shape without altering the stability of these robots. So using more complex designs and have more complex paths to follow while staying stable. So that was kind of interesting also results here. All right, done for CTCR. Let's jump to another kind of continuum robots. I worked also on magnetic continuum robots. That was also a big part of the collaboration with the ETH Zurich. So here we have robots that are composed of a flexible tube along which one or several magnets are embedded. And basically the goal is to generate an external magnetic field on this magnet in order to generate torques on them and then to deform the structure. So that's basically what you can see here, where the robot plays Quidditch going into different circles. So you have the robot, an example of robots here, a flexible tube with a magnet at the tip. And then the robot is placed into this much larger actuation unit, this magnetic navigation system, as we call it, that is composed of big electromagnets to generate a magnetic field around the robot. So basically, this actuation unit englobe the workspace of the magnetic robot here. So these magnetic continuum robots have also several advantages. We can also obtain quite small size manipulator under 1 millimeter. Again, it's just a manipulator. The actuation unit around is pretty big. We can achieve a large workspace with these robots and large bending angles because they're composed of soft material and they have this contactless magnetic actuation.
Another question for the magnetic ones.
Yes.
Those are the for robots like this, you practically can only control like one quote-unquote joint or only the end effector, right? Otherwise, there is no way if you put 2 magnets like the magnet, you cannot select between magnets. So, so basically, magnetic continuum robots are by design for just end effector control or some other single joint control.
Yeah, it's a very good comment. They are usually limited in the number of actuatable degree of freedom because it's difficult to. We could imagine. In theory, you could say, I put 2 different magnets at different locations and try to generate different magnetic fields at these 2 locations. But this is actually very challenging if you want to have a large workspace and have this huge variation of the magnetic field, let's say. So basically with a system like this, a big system like this, the field is almost homogeneous, not entirely, but homogeneous. So you just have control 2 degrees of freedom with this. But now the researchers working on this magnetic continuum robots try to increase the number of degrees of freedom by having either serial robot arm that carries magnets and that can be closer to the robot and have more different magnetic fields, or by iterating on this design of magnetic navigation system. So you're right, it's challenging. And currently in the state of the art, it's mostly like homogeneous magnetic fields, but it's kind of evolving towards this multi-magnet robots and control.
Okay.
Yeah, that's also what you can see on this graph, right? Like you see two magnets on the robot, and the two magnets have as basically subject to the same magnetic field here. So this softness of these robots is very interesting because you can achieve this large like workspace while they deform. But it's also like creating problem because the robot is significantly impacted by gravity. And when we are trying to deflect the robot can have this snapping phenomena, as you can see on the video. By the way, this is a quite small robot, which is very soft. But this phenomena could happen for robots at much larger scale where the gravity is significant. So this is a problem that we study for this particular kind of robot, but it can be actually applied to large scale continuum robots as well. And so these phenomena have been mentioned in the literature, but not studied. And so because like the spatial deformations and the magnetic actuation is quite complex to study analytically. So we applied our tool again to this particular case in order to study the robot motion. So if I start from my initial configuration and if I vary the orientation of my magnetic field B here, normally I should obtain this different bending configuration, and my robot should continue bending in a plane, as we can see on the graph here. But because of gravity, the robot will actually stop bending at some point, some critical point, and will prefer to fall in the direction of the gravity in one direction or another, and we have a branch point at this location here. So this was very interesting because we could show for the first time this existence of multiple configurations for these robots, and then observe this workspace reduction here. Because of gravity, we actually become unstable and cannot access all the deflection that we should normally access. And so we obtained these results, and we also studied the impact of now small perturbation on the robot, because the magnetic field has also a gradient. It's not perfectly homogeneous, and this gradient will apply some forces on the magnet as well. And we observed that following this small perturbation, the robot will tend to fall in one side of the graph or in another. So due to this unstable phenomena, small perturbation have a large impact on the robot shape, basically. All right, last but not the least, very recent work on a new kind of continuum robot, which we call the magnetic concentric tube robots. So here in this work, we basically try to combine both robots by assembling them concentrically. And then we obtain the robot that you can see here, that is composed of telescopic precurved tubes, and then an internal tube, which is actually an optical fiber with a magnet at the tip. And so we did this. We combined these two robots because to obtain their different properties. So having a small size manipulator with an outermost tube of 1 millimeter diameter, which can be used to perform this perfect follow-the deployment while being dexterous. So this structure has 7 degrees of freedom, and also in order to allow to to manage actively the elastic stability of the robot. And basically what we did is to try to find a simple strategy to manage this stability. So first of all, to consider a simplified case study for this robot where the inner tube is retracted. So the magnet in red is actually directly at the extremity of the concentric tubes. We put the tubes in we oppose the curvature, which is kind of the worst case scenario from a stability perspective. And then we apply magnetic field on these robots in a particular plane. And then in with theoretical work by perturbating the robot configuration around this specific configuration, and then analyzing the magnetic torques that are actually applied, we can detect and select magnetic fields that will tend to put the robot back to its initial configuration after the perturbation, which will have a stabilizing effect on the robot, or put this robot away from its initial configuration, which will have a destabilizing effect. And then that's what we try to validate numerically and experimentally. So we start from a robot configuration where we are almost unstable. So this is the blue curves here and the video that you can see here. So we are almost unstable theoretically, but in practice, we are a bit unstable at some point. You saw the jump of the robot during the rotation. And then by selecting appropriately magnetic fields, we can stabilize these robots during the rotation of the precurved tubes. So we can see on this green graph that we have just one configuration for one unique configuration for desired set of actuation inputs. Or we can try to provoke these unstable motions and to amplify the unstable behaviors for these continuum robots. So here we accumulate and puff. We jump with larger amplitude between two configurations, basically. Yeah, so that's all for the results. So as a conclusion, in this work, we propose a numerical framework for the stability analysis of continuum robots. And this framework allowed us to obtain new knowledge on the stability of concentric tube continuum robots during follow-the-leader deployments and the stability of magnetic continuum robots. And it allowed us to investigate an first active stability management strategy for concentric tubes using magnetic actuation. And all of these numerical results have been, we had the opportunity to validate them experimentally and to observe that we had good correlations between our prediction and the reality. Now I would like to end up quickly on some perspectives. So the current approach today is to try to avoid this unstable phenomena. By iterating on the design, you can try to limit the range of deformation and try to have a robot which is always stable. But of course, this will limit the robot performances because you will have a limited workspace, and this constrains the robot designs. So I think instead, one very interesting research area is to try to control these phenomena and to use them to obtain different kinematic performances, for example, by exploiting these different robot configurations. We could also modulate the stiffness of these robots. And so this is, we can discuss it later. It's quite longer to explain, but you could look at what we call negative stiffness mechanisms that exploit these elastic instabilities to modulate the stiffness. Or we could also apply impulse forces due to this sudden snapping to generate forces that are more important than the quasi-static forces. And basically, I really like this work that you can see on the video here, where they try to use this snapping to actually perform suturing during a medical procedure. So they could generate forces that are enough to penetrate tissue. But if you do it in a quasi-static way, then you cannot penetrate the tissue, and it's the robot that will deform instead. So that's pretty cool. Of course, there are a lot of challenges behind using this phenomena. So first of all, we saw that the way we have to predict this phenomena depends strongly on a priori knowledge of the system. So we have this kineto-static model. We need to derive a model to obtain this information, a model that has a certain accuracy. And also we consider specific case study and scenario, which we determined with some a priori knowledge of the system and of the robot behavior. The robot could have different way of being unstable, different maybe unstable phenomena that we did not detect because it's a more complex case or something like this. And also, like these results that we obtain are very sensitive to small perturbations, and these phenomena are in general sensitive to small perturbations, so that okay, or there are some limitation to our ability to predict accurately these phenomena to actually control them. All right, and last but not the least, we have a work with Jessica in preparation where we actually study another kind of continuum robots, which are tunnel-driven actuated this time. So if you are interested in that and learning how we can also use this unstable phenomena to do something cool, just look at this paper when it comes out. It comes out. Sorry. All right, I would like to end this presentation by thanking all the amazing people I worked with during my PhD, my beloved PhD supervisors from eCube and FemtoST, so Pierre Renaud, Quentin Robben-Rosso, and Nicolas Andreff, with also the supporting engineering staff, and also the multi-scale robotics lab from the ETH Zurich, directed by Bradley Nelson here, and Quentin Buller, with whom I worked closely. Thank you all for your attention. I hope you enjoyed the presentation, and I'm open to any question if you have.
Quentin, thanks so much. That's a super interesting talk, and for me, it's certainly a very, very new topic. Yeah, I hope you guys have some questions. I want to get started maybe with like another type of outlook. So as you start your own position, what are the topics that you will be working on, like, or what do you see as like interesting big challenges for continuum robotics that you would like to build a career on?
So I mean, I'm still working in continuum robotics, but I kind of changed direction as well. Taking inspiration from some what researchers in France want to work on as well. So the goal is, instead of like, I would say the initial idea is not to push to have a very hard node in continuum robotics and push it further, but rather to use continuum robotics to do something we couldn't do with traditional rigid robotics, and on a quite original topic, which is eco-design robots. So the goal, what I will be working on, is to try to design a robot which is the most eco-friendly as possible, and from a mechanical design perspective. So instead of using metal to actually build these rigid links that we see in industrial robots, trying to use biosource material, wood, or biosource gels that come from algae. And if we can do a robot which is entirely composed of this material, so which, if you don't want to have like standard joints, which is flexible, so have this like continuum structure that are made up of wood or of the biosource material, we could obtain a robot which is biodegradable, which is cheaper to fabricate, and the goal is to have a good accuracy and good performances at the same time, which is kind of challenges because we're using these new materials, and if you guys have some experience or try to work with wood, it's a material that moves with humidity and temperature, and they are which is not isotropic, which has like particular mechanical properties as well. So there are a lot of challenges in using these new materials for continuum robots. And then I have also other ideas. I think I like these stability questions too much to just not working on them. So I will probably try to include them at some point in these parallel continuum structures.
Okay, yeah, thanks. Any more questions from your own side? Okay. I think we have no more questions. Quentin, then let me thank you so much for your time and for having been with us this morning. It was super interesting, particularly to me. I'm super new to continuous robots, so all I know is either from Jessica or when I talk with you guys or see your demos. So it was a very fun presentation.
Nice.
Good luck with your new position and have a safe trip to France.
Thank you very much. Thank you a lot for having me. I always enjoy to present these kind of things. If you have any question in the meantime, don't hesitate to reach me. Even after I've left, I will be super happy to discuss that with you.
Okay, thanks so much. Thanks so much, everyone, for joining. Have a wonderful day.
Have a wonderful day, everyone. Take care.
Bye.
Thanks.
Thank you so much for coming.